Ever feel like our understanding of the universe is just, a tiny island in this vast ocean of unknowns?
Hmm.
Well, today's deep dive is going to be all about charting those uncharted waters. We're diving into Stephen Hawking's A Brief History of Time
Oh, excellent choice.
to explore everything from the Big Bang to black holes to the mysteries of quantum mechanics
Right.
to even the possibility of time travel.
Yeah, and trust me, even if you think black holes are something you find in a sock drawer,
Right.
this deep dive will leave you with some serious cosmic wisdom.
I love it. Speaking of wisdom, let's rewind way back to ancient Greece.
Okay.
You wouldn't think something as basic as the Earth being round was a puzzle, but figuring it out was a huge deal.
Oh, it was. And you know what's even more incredible? Around 340 BC, Aristotle didn't just figure out the Earth was round, he actually calculated its circumference.
Wow.
And get this, he was less than 1% off the actual value.
No way.
All that with just shadows and simple geometry.
Wow, talk about an aha moment. It really makes you appreciate the power of observation. But let's fast forward a bit from ancient Greece to the 1920s.
Okay.
This is where Edwin Hubble enters the scene and kind of rocks our cosmic world.
Absolutely. Hubble's observations were revolutionary. He noticed that galaxies aren't just sitting still, they're actually moving away from us.
Really?
And here's where it gets really interesting. The farther away a galaxy is, the faster it's moving. Imagine those expanding ripples in a pond, but on a cosmic scale.
Okay, I'm already seeing where this is going, the expanding universe.
Exactly.
But how did we go from expanding ripples to the mind-blowing idea of the Big Bang?
It's an incredible story, actually. Picture this. It's 1965, and these two scientists, Arno Penzias and Robert Wilson, are trying to get rid of this annoying static in their antenna. Turns out that static wasn't a technical glitch. It was faint microwave radiation
What?
coming from every direction in space. They had stumbled upon the afterglow of the Big Bang itself, the cosmic microwave background radiation.
Talk about a happy accident.
I know.
But I have to know, what does this afterglow tell us about the Big Bang?
So this radiation is essentially the faint echo of the universe's birth, the heat left over from that initial explosion.
Wow.
It's the most compelling evidence we have that the universe, everything we know, began from a single point.
Okay, so we've got this expanding universe, the Big Bang. But now let's talk about these cosmic heavyweights. Black holes. They're like the ultimate cosmic vacuum cleaners, right? Sucking up everything that gets too close.
That's a pretty good analogy.
Yeah.
Black holes are regions in space where gravity is so intense that nothing, not even light, can escape.
Wow.
Imagine a massive scar, much bigger than our sun, collapsing under its own gravity until it becomes so dense that it literally punctures the fabric of space-time.
So anything crossing that point of no return, the event
The
horizon,
event horizon is gone forever.
that's what classical physics tells us. But as always, the universe loves to throw curveballs.
And this is where things get really wild. Stephen Hawking, the author we are deep diving into today, actually made a groundbreaking discovery about black holes.
Okay, let me guess they aren't actually black.
You got it.
What's the twist?
Hawking discovered that black holes aren't completely black after all. It turns out they actually emit a faint radiation, now known as Hawking radiation.
Wait, but I thought nothing could escape a black hole.
Right.
How does that even work?
This is where quantum mechanics, the study of the super small world of atoms and particles, comes in.
Okay.
Imagine empty space as this bubbling, frothing sea of virtual particles that are constantly popping in and out of existence.
Okay.
When this happens near a black hole's event horizon, one particle can get trapped inside while its partner escapes as Hawking radiation.
So in a way, black holes are slowly evaporating, leaking energy into space.
Exactly. It's a mind-boggling concept. But this raises another question. If black holes can evaporate, what happens to all the information they've swallowed? This, my friend, leads us to one of the most perplexing mysteries in physics, the information paradox.
Yeah.
But first...
Okay, before we dive into that rabbit hole, let's back up for a second.
Sure.
We talked about the Big Bang, but something that's always puzzled me as well. What happened before?
Right.
And what caused this massive explosion in the first place?
Those are the million-dollar questions. And the truth is we're still trying to figure that out. But one of the leading theories is inflation. This idea that right after the Big Bang, the universe went through a period of insane exponential expansion.
Okay, how insane are we talking?
Imagine this. In a less than a fraction of a second, the universe went from something smaller than an atom to the size of a grapefruit.
Wow.
This might seem completely bonkers, but it explains a lot of the things we observe about the universe today, like why it looks so uniform on a large scale.
Wow, that is bonkers. But hold on, where did all the energy for this inflation come from? It's like the ultimate free lunch.
That leads to a truly mind-bending idea.
Yeah.
The universe might have zero total energy. It's like the ultimate magic trick, pulling a universe out of a hat with no initial energy cost.
Wait, what? Zero energy? How is that even possible?
It's all about balance. You see, matter and energy have positive energy, while gravity has negative energy. The mind-blowing suggestion is that these might be perfectly balanced, making the total energy of the universe zero.
Wow.
And if you could create a universe from zero energy, well, you've got the ultimate free lunch.
That is a lot to process.
It is.
So we've got this universe potentially born from zero energy, expanding at an incredible rate.
Yeah.
It's almost too much to wrap your head around.
It's definitely a lot to take in. But just when you thought things couldn't get any weirder, we have to talk about the world of quantum mechanics, the study of the very, very small. This is where our everyday intuition goes completely out the window.
Okay, so we're about to quantum leap into the realm of the very small. This is where things get really interesting, but also really weird, right?
Yeah. You could say that. Imagine a world where particles can be in multiple places at once, where the act of observing something can actually change what you observe.
It's enough to give you a quantum headache.
Yeah.
But seriously, this stuff is mind-boggling. One of the things that always trips me up is Heisenberg's uncertainty principle.
Right.
It sounds more like a spy thriller than a physics concept.
It does, doesn't it?
Yeah.
But it's one of the most profound ideas in quantum mechanics. Essentially what it says is that you can't know both the position and momentum of a particle with perfect accuracy at the same time. The more precisely you measure one, the fuzzier the other becomes.
It's like trying to nail down a cloud. But what does it all mean in the grand scheme of things? Why should we care about these quantum conundrums?
Well, for starters, it challenges our entire understanding of how the universe operates at its most fundamental level.
Right.
The deterministic world of classical physics gets thrown out the window. But here's the thing. These quantum effects aren't just confined to some subatomic realm. They influence everything around us, from the way stars shine to the technologies we rely on every day.
Okay, I'm starting to see how this all connects, but before we lose ourselves in the quantum foam, I want to circle back to something we touched on earlier, the life cycle of stars. Hawking explains how these celestial giants are born, live, and die in this amazing cosmic ballet.
It really is an incredible story. Picture this. A giant cloud of gas and dust, mostly hydrogen, just hanging out in space. Gravity starts to pull this material together, and as it collapses, things get hot, really hot. Eventually, the core becomes so hot and dense that hydrogen atoms start fusing together, forming helium and releasing an incredible amount of energy.
And bam, a star is born. This nuclear fusion is like the star's engine, right? Powering it for billions of years.
Exactly. But just like any engine, it eventually runs out of fuel. What happens next depends on the star's size. Smaller stars, like our sun, will eventually expand into red giants, shedding their outer layers and leaving behind a dense core called a white dwarf.
So it's like a stellar retirement plan.
Yeah.
Shrinking down and cooling off after a long, bright life.
You could say that. But for more massive stars, things get a lot more explosive. When they run out of fuel, they collapse so violently that they trigger a supernova, an explosion so bright it can outshine an entire galaxy.
Now that's going out with a bang. But what's left behind after all the fireworks?
It depends on the mass of the star. Sometimes the core collapses into a neutron star. Imagine the mass of the sun crammed into something the size of a city with the density so high that a teaspoonful would weigh billions of tons.
Okay, that's just mind-boggling. But what about the really massive stars?
For those behemoths, even a neutron star can't withstand the crushing force of gravity. Instead, they collapse into, you guessed it, a black hole.
It's incredible to think that these objects, which seem like something straight out of science fiction, are actually the end result of a star's life cycle. But speaking of science fiction, let's talk time travel. Could we ever actually build a time machine, or is it just a fantasy?
Well, Einstein's theory of general relativity suggests that time travel might actually be possible, at least in theory. You see, according to Einstein, gravity isn't just a force, it's a curvature in space-time.
Okay, hold on, space-time. What exactly does that mean?
You can think of space-time as the fabric of the universe. It's a four-dimensional structure where space and time are intertwined. And just like a bowling ball placed on a trampoline, curves, The fabric of massive objects warp space-time, and this warping is what we experience as gravity.
So instead of a flat trampoline, we're living on a cosmic trampoline that's constantly being warped and stretched by massive objects.
Exactly. And this warping doesn't just affect space, it affects time, too. Time actually slows down the closer you are to a massive object. This isn't just a theory, it's been experimentally verified.
Whoa. So does that mean time travel is really possible? Could we create a warp in space-time and travel to the future or the past?
That's where things get even more complicated. Some physicists believe that extreme warping of space-time could potentially create what we call wormholes, which are essentially shortcuts through space-time.
So you're saying we could jump in a wormhole and travel to a different point in time, like hopping across cosmic stepping stones?
In theory, perhaps. But there are some major caveats. For one, we've never actually observed a wormhole, and it's not even clear if they are stable enough to travel through. Plus, there are all sorts of paradoxes associated with time travel, like the classic grandfather paradox.
Right. If you go back in time and accidentally prevent your grandparents from meeting, you wouldn't be born, which means you couldn't have gone back in time in the first place. It's enough to make your head spin.
Exactly. But even if we never build a time machine, the very idea of it forces us to grapple with some of the most fundamental questions about the nature of time causality and the meaning of our existence. And that, I think, is part of what makes A Brief History of Time so captivating.
It definitely makes you think big. One thing I find particularly intriguing is this idea that the laws of physics might be different in other parts of the universe, or even in other universes. Is there any evidence for this, or is it pure speculation?
That's where we enter the realm of cutting-edge physics and cosmology. There are some theories, like string theory, that suggest the existence of a vast landscape of possible universes, each with its own set of physical laws.
So there could be a universe where gravity works in reverse or where time flows backward.
It's a possibility. But it's important to remember that these are just theories at this point. We don't yet have any observational evidence to support them. However, the very fact that these ideas are being seriously considered by physicists speaks to the sheer strangeness and wonder of the universe we live in.
It's like our minds can barely scratch the surface of what's out there.
Absolutely. But that's what makes this journey of cosmic discovery so exciting. Every new piece of the puzzle just raises more questions, propelling us to explore further.
We've covered so much ground in this deep dive, from the mind-blowing scale of the cosmos to the head-spinning world of quantum mechanics. It makes you realize just how much our understanding of the universe has evolved since, Aristotle's time.
It really does.
Yep.
And we owe a lot of that evolution to brilliant minds like Stephen Hawking, who wasn't afraid to ask the big questions and challenge our assumptions about how the universe works.
Speaking of big questions, there are still so many mysteries left to unravel, like what happened before the Big Bang? What lies beyond the edges of the observable universe? These are questions that keep physicists up at night.
They certainly do. And while we don't have all the answers yet, we're constantly developing new tools and theories to probe deeper into these mysteries. Who knows what incredible discoveries await us in the future?
It's both exciting and humbling at the same time. On one hand, we're making incredible strides in our understanding of the cosmos. But on the other hand, we're constantly reminded of how much we still don't know.
It's that sense of wonder and curiosity that drives scientific exploration. And it's not just about the big discoveries, it's about the journey itself, the constant quest to expand our knowledge and push the boundaries of human understanding.
I couldn't agree more. As we wrap up this deep dive into A Brief History of Time, I'm left with this profound sense of awe at the sheer scale and mystery of the universe. It's a reminder that we're part of something much greater than ourselves.
It is. And while we've explored many fascinating concepts today, from the birth of stars to the bizarre world of quantum mechanics, I want to leave you with one final thought to ponder. If the universe had no beginning and will have no end, as some theories suggest, what does that mean for our place in this grand, ever-evolving cosmic story?
It's a question that each of us has to answer for ourselves. But one thing is for sure, our journey of exploration, both as individuals and as a species, is far from over. There's a whole universe out there waiting to be discovered, and who knows what mind-blowing revelations await us just beyond the horizon.